as you probably know and may already have experience with, if you warm up something, it will get bigger. In fact, it gets bigger in all dimensions, and right now we're worried about it getting bigger in the length dimension. And we can calculate this as thermal deflection equals a coefficient of thermal expansion times the change in temperature times the length. In fact, the thermal strain can be calculated as simply alpha delta T, which is all fine and simple and easy, but if we have a part that's constrained on both ends so that it may not expand, we would like to know how much force is required to do that. And so let's say that, as before, this has some coefficient of thermal expansion and some length, and we give it a change in temperature. And as we saw before, we can use the principle of superposition and break this into two scenarios because of the linearity of the effect. And in one scenario, we have the change in temperature and we get the increase in length, and also we can look at the force to eliminate that increase in length. And as we've done before, this is delta T equals alpha capital delta T L, and this is deflection due to a load P, and that is PL over AE, and so this is the principle of superposition again, and then we can use a compatibility equation that delta T plus delta P add up to 0. And so we get alpha delta T L plus PL over AE equals 0. We can cancel the L and solve for P. P equals minus alpha delta T AE. Super simple. And if we plug in some numbers, let's suppose that alpha is 6.60 times 10 to the minus 6 per degree Fahrenheit. And let's pick a change in temperature of plus 60 degrees Fahrenheit. Use an area of 0.25 square inches, and let's let this be steel, so 29 times 10 to the 6 pounds per inch squared for a modulus of elasticity. And so the load is going to be, the minus is for compression, 6.6 times 10 to the minus 6, 60, 0.25, 29 times 10 to the 6, and when you multiply that all together, you get 2,871 pounds. Quite a bit of force. If you had this piece of steel and warmed it up by 60 degrees, you would need almost 3,000 pounds, a ton and a half of force to keep it from expanding. And that's it.